Bismillahirrahmanirrahim. Today we are going to do the mathematical part of chapter 4. And before going into the numerical part, I would like to revise few important points of our chapter 4 so that you might have an idea that what was going on and what was banding and what are the important expressions and formula you can use to solve those numerical problems. Right, so this is a quick review of the chapter 4, and first we discuss what the neutral axis. Neutral axis is basically the axis along which compression and the tension takes place, and generally normal to normal phase, which in the direction of the in which direction the force is being applied. Right, then we discuss the centroid. Centroid is the geometric center of the shape. How it is calculated, we divide the shape whole shape into different areas, like in this particular case a1, a2 and a3. These are areas. We calculate the areas of that shape. We calculate the centroid of that particular shape, which is generally, because these are all rectangles, so it will be to each rectangle would have a centroid at the center of that centroid, and then we define an axis, and we subsequently go each shape accordingly to calculate the y, and then we multiply the centroid with the area, uh, that is this one, right? And then we sum up all area into centroid and divided by sum of all the area, so we get the information about the centroid of that particular whole shape, right? Then we discuss moment of inertia, or the second moment of area. These are the expressions. These are the fixed expressions for the rectangle shapes. Likewise, we can have fixed expressions for the circular shapes, semicircular shapes, square shape, rectangle shapes, right? These are the common shapes which we use during the numerical sections of this part of this chapter. So there are standard expressions which are available to calculate the second moment of area of that particular shape, right? And then we use parallel axis theorem. Parallel axis theorem is primarily used when we don't want to calculate I about the centroid. Means if you want to calculate any I at any point other than centroid, then you have to use the parallel axis theorem. So we will use in one of the numerical examples as well. So it is the sum of the I, that is the against centroid, and then area of the particular shape, and at the and the d is basically the distance from the section centroid, that is c. So we add up both these quantities, so we get the I of that particular shape about any other point other than the centroid. Then we discussed different aspects. Then we have a beam. When we apply a positive moment. Positive moment means if this is y-axis and this is x-axis, so any bending that is in the positive y direction, that is called positive, or any bending that is along the negative y-axis, that is the negative bending. This is the sign convention for the bending, right? So we doing all the mathematics, we end up that epsilon x is y minus rho. Rho is basically the area of the curvature. uh, Rho is basically the area of is the radius of the curvature, this one, and y is the distance from the neutral axis, right? This is the y. This is the neutral axis we have, and then this is basically the y. Any other axis, these are dotted axis, the y is, and maximum is obviously this axis, this distance is c, where bending will be maximum. That bending may be compressive stresses or the tensile stresses. In this part it will be compressive, in this part it will be tensile one, right? So the expression for any point other than c will be a strain will be y over rho, and for maximum, obviously maximum will be at the c on positive side or the negative side. So E max will be c minus rho, or E max may be c over rho. In this particular case, it will be a tensile force. In this particular case, it will be a compressive forces, right? Another expression which is very important is the relationship between the epsilon at any other point other than C with respect to epsilon max, the ratio of the y over C, right? C is the maximum distance, y is the distance any other point, the maximum other than the maximum one from the neutral axis, right? By doing all the mathematics, then we end up with this expression mc over I. This is again very important one. This is for the maximum because C is the maximum distance from the neutral axis, so obviously sigmas will be maximum on the top or on the bottom surface. Top it will always be a compressive one, and bottom it will be a tensile one if it is a positive bending there. In case of negative bending, it will be opposite to that, right? Or sigma other than any point other than C, obviously it will be not the maximum one. So instead of C, you will be using y over there. So these two expressions with this one, or in terms of epsilon, it would have same y over C epsilon max. So you can use, so these are the some of the important expressions which we can use during all this mathematical part, right? And we had the section modulus. This is the section modulus for a rectangle one, and we saw the body which are having larger height would have the more S. More S means lesser stresses, normal stresses will be there when moment will be applied, because section modulus is opposite to the section modulus is inversely proportional to the sigma max value, right? And then in the end we calculated the curvature, right? Rho we know is the radius of curvature. Inverse of the rho, 1 over rho will be curvature, right? Elastic for the for a bending beam. So this again, this is very important one. M over EI. M is the moment, E is the Young's modulus, and I is the moment of inertia, second moment of area. So whenever we want to calculate curvature or the radius of curvature, we can use this expression. So let's start from the example 4.01. So there is a bar, rectangle in shape, zero point 0.8 into 2.5 inches is subjected to the two equal and opposite couple moments acting on the vertical plane of the symmetry of the bar. Determine the bending moment determine the bending moment M that causes the bar to yield. Sigma y is basically yield strength, or the yielding stress is 36 ksi. Obviously we never want that stresses go beyond this yield point. We have already discussed many times that yielding point is the point of the failure, right? So we don't want that stresses, irrespective of that, any stresses means the final state of stress, uh, all the all the normal stresses as well as all the shearing stresses, none of the value should be greater than the yield strength, normal yield strength or the shearing yield strength, right? In case of shearing yield strength will be there. In case of normal yield strength will be there. So in any case, we don't want to have the stresses irrespective that they are tensile or they are normal or they are shear, they pass their yield strength value, because beyond the yield strength value they will go into the plastic range, and plastic range is assumed to be the failure for us, right? So what we will do, we will simply calculate. We know that sigma is mc over I, right? This is the sigma max value, right? So sigma max C, we know that C is basically the distance from this particular point, because this is a rectangle shape. So neutral axis will be over here, right? And C will be on 1.25 upward, or C maybe 1.25 downward, because this is a positive one. Moment is the bending is positive. We can when you will apply this moment, it will go bend like this one, and we know because this is the positive y direction, so assume that this is the positive bending, right? So maximum will be I, we can calculate from the rectangle shape, and we know I is equal to bh cube, B is 0.8, H is 2.5. So this will be a I for that one. This is this expression MC over I, right? So I is 1.042 inch square. C is 1.25 because center is the neutral axis, and above the neutral axis it will be 1.25 into 36 ksi. So moment will be 30 kips inch. This moment will be that maximum moment that can be applied. Otherwise, it will go uh, beyond the your yield strength value, right? So this is how you can calculate the so sigma max will be, in this particular case, sigma y will be sigma max, because we don't want that our stresses will be going beyond this one. So 36 cases, so this is the maximum amount of moment that can be applied on this particular body, right? Okay, fine. Let's go to 4.02. Now you have a semicircular shape, right? Aluminum rod, semicircular cross section, radius is 12. Rho, radius of curvature, means the radius of curvature is 2 point. This is not the curvature, this is radius of curvature, right? So radius of curvature is 2.5 meter, right? And then you have you can use E, Young's modulus is 70 GPa, gigapascal, right? So this is the Y bar. Y bar is basically the centroid. Centroid of a semicircular shape is, you have this expression. This is a standard expression for a semicircular one to calculate its centroid, right? This is the centroid. So it will be 5.093. This will be the centroid of this. C point will be 5.0393 meter from the millimeter from the this bottom surface, right? This is the bottom surface. So if the radius is r, that is this one, this radius is r. So if y bar is 5.9093, so C maximum from the centroid, that will be r minus y bar. So r is the radius, that is 12, minus C minus y bar is 5.093. So 6.907 will be the C, and this will be this one. This, you can see, this is the C, right? So C is the surface, C is the distance at which the surface, existing surface, will be having some sort of maximum stresses, normal stresses. It may be a compressive, or it may be a tensile, depending upon the nature of the shape of the one. For example, in this particular case, obviously when it will bend like this one, so you will have on this surface it will be tensile one, and this surface it will be compressive one, right? So epsilon maximum strain will be C over rho. This expression we have already seen. So this will be maximum strain that can be produced, right? And then epsilon m will be Hooke's law. So sigma m will be E epsilon m, and you will calculate this one. Since this is a positive quantity, so it means it will be a tensile one. So this will be the at this surface, right? So if we want to calculate the compressive stress on this surface, because it will be, if this is tensile, so compressive will be over here, over here on this surface, right? So compressive will be minus y bar over C sigma m. This expression we have already seen. So by doing all this, we will end up with the 142.6 megapascal. So obviously this will be the amount of compressive stress that will be on this. This negative sign just showing that these are the compressive stresses, right? Fine. Okay, fine. This is again an example. Example is, I think, 4 point something. I can't see over here what the exact example is, but it's from the book, obviously. So what is it saying? Rectangle tube. This is a tube, right? Rectangle tube means it is a hollow one, right? Rectangle tube shown extruded from the aluminum alloy, from which sigma yield is, normal yield strength is 40 ksi. Ultimate stress is 60 ksi. E, Young's modulus, is this one. Neglecting the effect of the fillets determine bending moment M, for which the factor of safety will be 3.00, and the corresponding radius of curvature, right? for the tube. We want to calculate rho, not the 1 over rho, right? But we have the expression for 1 over rho, so we will take that and we will take the inverse of that. By the end of the day, we will calculate epsilon, right? Okay, fine. How to calculate I? Because this is the shape for which we want to calculate I. Since it is a rectangle one, so we will take external, that is the 3.25 by 5. This is one rectangle minus the area of this rectangle, that is 2.75 into 1.45. So using the same expression, I 1 over 12 of this minus 1 over 12 of this, so we will get the I for this shape, hollow tube, which is in the rectangular cross section, right? Now allowable stresses we have already seen. Ultimate tensile strength or ultimate normal stresses divided by the factor of safety, that is the allowable one. Maximum which we can allow is 20 ksi. We can't go for this 20 ksi, right? Since this is less than sigma y, so we are safe. So we are safe because these are the maximum allowable stresses that can be applied, and this is less than sigma y value, yield strength value, so we are safe. So we don't need to worry about it. So we are still operating in the elastic range, and elastic range we know Hooke's law applies, so we can calculate accordingly the stuff, right? Now, what is C? C is how, because this is a regular shape, rectangle shape, so we know C will be existing in the center of that one, right? Since it is the height is 5, so it will be at centroid will be at 2.5 inch from the bottom of that. So we will do this. This is the C, and we will place x-axis over that. So this is our reference axis now, right? So our reference axis is existing at the centroid, and centroid is basically existing at the 2.5 inch from either side, because this is the regular shape. It doesn't matter okay, you measure it from the bottom or you come from the top. Sigma allow, we know mc over I, and m is basically sigma allowable I over c, and sigma allowable equals to 1.97 inch 4 over 2.1, and we can calculate m over this one, right? So for this allowable, so we cannot go, so we required moment is basically 110 Gibbs inch. So this is for having this shape and existing the centroid existing at 2.5. So this is the allowable. This is the moment which we can maximum apply that that would to create this sigma allowable, right? So bending moment m, for which the factor of safety will be 3. So if you want to keep a factor of safety 3, so this is the maximum allowable moment that we can apply on that particular shape to get these stresses and these stress values, that is 20 ksi, right? Now we want to calculate radius of curvature. We know 1 over rho, the curvature is m over ei. Moment is known 103.8, e known over here, and I known over here. So by doing this, we will end up this. Since this is 1 over rho, so we want to calculate rho, so we will take the inverse of this, so it will be 110.4 feet. This will be the radius of curvature. Radius of curvature will be, if this is a shape, finding one, so this is the radius of curvature for any particular shape, right? This is the one method. Another alternate solution is, the easiest one is, we know that Hooke's law, since we are operating in the Hooke's law, our sigma y value is sigma allowable value is less than sigma y value, so we can use this expression sigma e over epsilon, right? So from there we calculate epsilon, and rho, and the expression for epsilon, maximum epsilon c over rho, is known to us. From there we can directly calculate the rho as well, right? So again, both expression come up with the same solution of 110.4 feet for the curvature. Right. This is a different, a little bit different from the other one because now we don't have the regular shape. Right now we have a T shape, so it does not have the symmetry about x-axis if this is x-axis, right? So how we calculate the I, then we need to calculate sigma, and then we calculate the radius of curvature. The trick over here, the difference of this is that since it is not a regular shape, so C will not be existing at the center. C will be existing at another point other than the center of this one, right? So we'll have to calculate where the C exists. So how we will calculate? Again, we have two shapes, right? One is this shape and other one is this shape. Although these shapes are the rectangle in sections, so I shouldn't be the problem for that, right? Okay, fine. These are the two shapes. One shape having the area 20 into 90, that is equals to 1800 millimeters square. Other shape is 40 into 30, 1200 millimeters square, right? Since these are the rectangles, so from each rectangles, we know that the centroid will be existing into the center of that one, right? So for one shape one from this bottom, because at this we have taken this is x-axis, right? So from here we can see that y1 bar is at the 50 and y2 bar for the second shape from this reference is 20. So 50 and 20 are the centroidal position for the shape 1 and shape 2 from this x-axis, right? So y bar a is 90 into 10 raised to power 3 and 24 into 10 raised to power 3. We will sum up all these areas and sum all these uh, second moment of areas, right? The second moment of areas is basically 140 10 raised to power 3. Sum of all the areas will be 3000. So we will divide this both and we will end up 33. Now this is the 38 is the point at which this centroid is existing, right? And it is a little bit below from this surface, from this surface. This surface is from bottom. This was 40. Now it is at the 38, right? A little bit lower than the existing one. So centroid is not exactly existing at the center of this shape. So it is somewhere uh, at the 38 from the reference, right? So this is the y bar of this whole shape, that is at the 38. Now we want to calculate the I for this one. I, since it is not at the center, so we are interested to calculate this I. So I at that particular shape, right? At x bar now. So what we will do now? We will use parallel axis theorem. Parallel axis theorem says that I sum of all the i's plus a into d square. Fine. So there are two shapes now. One is shape 1, one is shape 2, and one is shape 1, right? So for shape 1 is 1 over 12, 90 into 20. This is the again 1800 multiplied by the plus 18 and sorry, I is equal to bh cube. B is 19, h is 20, 10 raised to power 20 to 3 raised power 3 plus a into d. Area is again 1800, this one, multiplied by the 12, right? 12 is this distance from the centroid to the center of this, right? The center of this initially it is at the if this is at the center and it is at the 38, 38, and then you have to calculate 38 minus 50 will be 12, and 38 minus 20 will be 18 for the second shape, right? Because this is 50 and this is 40. So it is 25 and uh, it is 20, right? Fine. So so 38 is basically these are the distance from the centroid, and centroid is existing at the 38 one, right? So by summing the whole this area, so we will end up with this I at 868 into 10 raised to power minus 9 meter 4. So this will be the I for this particular shape. Fine. So now what we will do? Now we have to calculate the C of A and C of B, right? C of B, C of A, CA is the maximum distance from the centroid of this surface A, that is the outermost top surface, and distance C of B is the distance from the centroid to this surface B, that is the bottommost distance from the centroid. These distances are because these are the surfaces. A and B are the surfaces where the forces will be maximum, normal stresses will be maximum, and we know MC over I is the standard expression to calculate the bending, calculate the stresses. So the surfaces, the stresses, normal stresses at surface A will be MC over A. M is known to us, that is 3 kilonewton meter into 0.00 0.022 meter will be the distance from the, it should be in millimeter, obviously it is 22 millimeter and 38 millimeter in the meter, because kilonewton meter, so we have to convert this into the meter one, right? So it will be 0.022 meter for the C, that is the distance from the centroid one, and for surface B, that is 0.038. This is the distance of the surface B from the centroid, and divided by 868, that is the I for this shape we calculated on the previous slide. So we will come up with the 76 megapascal and 131.69 megapascal for that one, because this is the radius curvature, this is the rho. When moment will be applied, so it will get this shape, that is the negative one. So negative one means top surface will be in tensile one, and the surface lower will be on this surface B, this point B, this is point A. So it will be A surface will be in the tensile one, so it is positive one, and B surface will be in the compressive one, so it will be negative, showing the expression for that, right? And for the radius of for the curvature, we know this is a standard expression, 1 over m over EI. By doing all this, we will end up with this 47. So rho in this particular case will be this rho will be 47 for this 47.7 meter for this particular shape, when 3 kilonewton meter moment will be applied on this one. This is the exercise problem 4.4. Again, we have this shape. This is a regular shape, and we will calculate I. I will be calculated in a way that this is the a rectangle shape, this whole rectangle minus a complete circle out of it, right? And the circle and that radius is given, so we can calculate I over BH cube. This is the whole shape, 100 into 80, and radius of curvature is pi by 4 r power 4, right? This is for the r, this is the I for the circle, complete circle, right? So we will subtract the rectangle from the eye of the circle, so we will end up the final eye of this particular one, right? Since this is the regular shape, so we will have the centroid at the center of that shape, and C surface will be existing exactly above from the centroid. So since this is the 80, so from this surface, these two surfaces will be at 40 millimeter on either side, right? So these are the 40. These are the two surfaces which will be going under tensile and the compressive loading. And sigma we know is mc over I. M about z-axis, because moment is being applied about the z-axis in this particular case as well. So sigma I over c. So the moment we will apply is basically 2.38 kilonewton will be the moment that will be applied to create this sort of forces on the surface. Last problem is 4.14. We'll have to do some mathematics over here. You can understand what's happening over here. dF is, this is what we have already done, sigma x dA. This is the standard force which will be applied on a smaller area, dA. So sigma x we know minus my over I dA, and when we will do the simple mathematics. So force, net total force by taking the integral of all the small forces that are being applied on the small areas dAs. So we will take the integral to calculate the total force, and by doing mathematics we will go come minus m over I y bar a bar. Y bar is no, I know that this is the basically the moment of area, right? Fine. So first we need to calculate what. So to calculate the total force, what we need m I y bar a bar, right? So first we calculate the I. Since it is a rectangle one, so we will take the I of the rectangle minus I of a smaller rectangle. These are the two rectangles which will be subtracted from that one. So complete rectangle is 6 inch by 7 inch, and a smaller rectangle is 4 inch by 4 inch. So we will calculate the individual eyes and we will subtract them, and we will end up with this 150.17 inch 4. That will be the one which will be your eye for this particular eye shape beam, right? M will be the moment that will be applied, and this value is given to us, that is 50 kips. Now area of the top flange, we know 6 top flange. This is the top flange, right? The area of top flange is 6 into 1.5, so it is 9 inch square. Y bar is basically the centroidal distance of this shape. This is the now axis from which we want to calculate. This is the C. So what will happen? So this amount is 2, because it is in the center of the center web. So it is, if it is 4, so this distance from this distance to this distance, it is 2, and this is 1.5, so it will be over here. Centroid will be in the half of this shape, right? So it will be 0.75. Half of the 1.5 will be 0.75. So from this, the top web centroid will be existing 2 plus 0.75, so it will be 2.75 inches. Likewise, this is the half web, the second part of this question. On the portion, shaded portion of the web, that is the half web. So why in this particular case will be, this is the shape on which it is existing, right? So if this is the centroid at C, so this is the shape we want to calculate. Since it is the whole area is 2, so it will be at the 1, right? So y bar for the half web will be 1 inch. So force, by putting this value minus m over I y bar a, so we can calculate the total force on the top flange and the bottom flange, or the half web, right? Area again is known to us, it is 2 by 2 inches. So this is the 2 by 2 inches. This is the 2 by 2 inches, and 1 inch is basically the centroidal position. So F will be 50 kips inch divided by 150.17 inch I of that one. Uh, Sorry. Right? So F will be F at the half web will be 1.332 kips, and F at the top line will be 8.24. Right? So this is the problem 4.14. So this is your assignment 3. Please go through it. I'll post this as well. 4.1, 4.5, 4.10, 4.15, and 4.24. This is your third assignment from the chapter 4. So go through it, and then we will end up with this. With this chapter. So finally, we are done with this chapter. So in next lecture, we will start our chapter 5. That is the bending moment and shear force diagram. So we will go ahead accordingly in our next lecture. Thank you very much.